A very good day to the lecturers. My name is Tae Singh from Group 6. Now, we will be presenting our findings on closed-loop speed control of a DC motor. A DC motor is one class of electrical rotating motors that transform electrical direct currents into mechanical energy. In a closed-loop control system, the control action from the controller is dependent on the desired and the actual process variable. In the case of the boiler analogy, this was utilize a thermostat to monitor the building temperature and feedback a signal to ensure the controller output maintains the building temperature close to that set on the thermostat. A closed-loop controller has a feedback loop which ensures the controller exerts a control action to control the process variable at the same value as the set point. For this reason, closed-loop controllers are also called feedback controllers. The main objective of our project is to design a proportional P controller that regulates the angular velocity of the motor such that it remains constant despite the presence of unmodeled dynamic, noise, and perturbation with the target specification below.
For the tachometer calibration, we can plot a graph by using this data, and we can find the slope of the line which is equal to our KT of 0.0489, and we will sub this value into our equation to get the output voltage of 2.048421 volt.
So we use the model as above P6L1 to illustrate the system with the aid of program Simulink. To operate the system, we set the input voltage as 5 volt, then we run the system. After that, a field of data can be obtained from the model. We can see from the oscilloscope. From the graph, we can estimate the motor response characteristic. A few characteristics which is important is listed in the table. The next step is to find KDC, which is the DC gain of the motor. We use the final value theorem to find the KDC. Finally, we found that the KDC of the motor is 0.292. So we can define the transfer function of the DC motor as below. Taking the inverse Laplace transform, you can get the transfer function in time domain. So to test the motor is operating correctly, we set a steady state speed motor to 400 RPM. So from the formula of motor equal speed of motor equal to KDC time input voltage, we found that the input voltage required is 145.45 voltage. To prove the motor in the model L1 is operating correctly, we set the V input equal to 145.45 voltage. After running the motor, we found that the tachometer reading show us 400 RPM. So it's synchronized with the set point that we set previously.
For the closed loop transfer function and by using the final value theorem and for the statistic error which is equal to plus minus 20%, we can find out the Kp is more than or equal to 218, and we can run the Simulink by using this voltage input. After that, we can use the graph data to find the percentage error and our maximum overshoot.
So we can see that by using the previous method, which is the final value theorem, we can find the Kp is 281, but it only satisfies one of the specification, which is the steady state error. But for the maximum overshoot, it's already exceed the 45%. The other method to identify the Kp is by using the root locus technique. We plot the root locus by using program MATLAB. First, we key in the open loop transfer function GS into the MATLAB, then plot the root locus. From the root locus, we can set the damping ratio by using the maximum overshoot that have to be achieved, which is 45%, we see that the damping ratio required is 0.246. So from the root locus, we can find the Kp have to be less or equal to 8.56. So we design that the Rv is equal to 75 ohm, while the R5 is equal to 10 ohm. After we set up the model L2 with the reference set point motor speed equal to 25 radian per second, its corresponding input voltage 1.225 voltage. The error response VE was shown in the figure below. From that, we can see we calculate the steady state error by using the formula, but unfortunately, we found the steady state error is 88.98%. It's already exceeds the specification, which is 20%. So we can conclude that from both methods to find Kp, we cannot satisfy all of the specifications, even either with Kp equal to 281 or Kp equal to 8.56.
This is model L3A, which is a plant response without feedback control when subjected to a disturbance t more than or equal to 5 seconds, where model L3B is with feedback control. After we inserting the input voltage into both models, we can see that the response experiences a jump at t equal to 5 seconds, which is affected by the disturbance. By comparing the response in model L3A and L3B, we can see that the effect of disturbance is much smaller in model L3B.
Through the process, we found that the gain in tacho generator is 0.0489, while the gain of the motor is 0.292. And the above are the open loop transfer function GS and the closed loop transfer function TS. To find the controller proportional gain, we will use final value theorem and root locus technique. Above is the value obtained through the root locus technique for two different cases. From the table, even if the maximum overshoot can be achieved to be smaller than 45%, but the steady state error is to be 88.9%, which is much larger than the specification, which is 20%. So we can conclude that the P controller cannot satisfy all the specifications set earlier, neither the controller proportional gain to be greater or equal to 281 ohm, nor the controller proportional gain to be smaller or equal to 8.56 ohm. By comparing the two cases above, we would like to choose the controller proportional gain to be 281 ohm. So far, it can be observed that the P controller cannot satisfy all the specifications required. So, we decided to use a PD controller to improve the stability of the plant by adding a derivative control to reduce the overshoot of the plant response. By using Simulink, we modified the model L2 into as figure above. Using the controller proportional gain to be 281 ohm, we managed to propose a PD controller which is able to meet all the specifications that we required. The value of the specification are stated in the table above.
Conclusion, we designed a proportional P controller that regulates the angular velocity of the motor such that it remains constant despite the presence of unmoduled dynamics, noise, and perturbation. The main usage of the P controller is to decrease the steady state error of the system. Our P controller design needs to satisfy the three target specifications, which are steady state angular velocity equal to 25 radian per second, steady state error equal to plus minus 20%, and maximum overshoot less or equal than 45%. Obviously, the steady state error is not be affected significantly after adding a derivative controller, and the transient response was improved after a PD controller is used compared to a P controller. Finally, we successfully proposed a PD controller to fulfill all the three target specifications.